All right, so welcome everybody. This is the Flow seminar. Well, Flow stands for Federated Learning One Word Seminar that was created to provide a global online forum for the dissemination of latest scientific research in all aspects of federated learning. Today, it's my great pleasure to introduce you our speaker, Peter Richtarik, who is a professor of computer science at KAUST, where he leads the optimization and machine learning lab. Through his work on randomized and distributed algorithms, he has contributed to the foundations of optimization, machine learning, and also course federated learning. And he's also a founder of the Flow seminar. Great pleasure to have you speaking, Peter. Please, floor is yours.
Thanks, Samuel, for the nice introduction, and thanks everybody for attending. As Samuel said, feel free to interrupt me at any point in time. I want to have discussion. I don't want to just leave the questions till the end. And I don't know how long I'll be talking, so I might actually go longer than an hour. We'll see how that goes. In that case, I hope at least Samuel is going to stay around to record me talking to an empty room. We'll see how far we go. So the topic for today is clearly related to federated learning, but it's something else from what I've talked about in the past. So in the past, talk about communication compression or local training or heterogeneity of various forms. Maybe Edward talked about Byzantine robustness. So we covered a lot of topics. I'm not sure if we covered any topic on asynchronous optimization and how this relates to federated learning. So I'm assuming this is the first one, and I want to explain how asynchronous optimization is related to handling device heterogeneity and whether going asynchronous or crazy asynchronous, you'll see what I mean by that, full-blown asynchronous is the right way of handling device heterogeneity. What kind of device heterogeneity, and is it correct or not, and so on and so forth. So this is really the topic for today. We worked on this for the past 2 years roughly, and we written a number of papers, and some of the co-authors of these papers are here on this nice photo from KAUST. So this is our lab, maybe from, what is it? Is it about a year ago? Can somebody on the photo confirm when this was taken? Is anybody here in the room? So Arto, are you here? Was this like roughly a year ago, or is it even more? Anyway, so this is a fairly recent snapshot of the team. Some people already left, some more people joined. And you can see Sasha Turin, former postdoc, who is now faculty and a researcher in Moscow, and Ivan Ilin, Arto Maranian, Kaya Gruntkovska, Omar are co-authors on various papers related to this stream of papers. All right, so first, very, very brief introduction. Maybe I should have deleted these slides, not really necessary, so I go very quickly through this. So federated learning started almost 10 years ago in this collaboration with the Google team led by Brandon McMahon and my former PhD student Jakub Konečný, who seems to be enjoying his life in Italian Alps at the moment. There was this Google AI blog from April 2017, which coincidentally is roughly the time when I joined KAUST as faculty. And this, I'm not going to read through this, and it's probably not even possible. It's a very tiny print, but this Google blog mentions 4 papers. 2 of these are collaborative works with Jakub and the Google team. This was the first federated learning app, next word prediction. I don't think I have to say anything about this. We've been working on federated learning ever since and wrote a bunch of papers. This is not the latest snapshot of my website, but I just wanted to highlight that maybe 50% of our activity still is in this domain. There's lots of interesting questions we can ask. So it's a very potent source of inspiration for research. Okay, so federated learning was also mentioned. This is from already 5 years ago as one of the futures of AI and machine learning. And in fact, one can see this in methods such as DiLoco, which recently have been gaining some interest in the large language models community. You would see lots of the stuff that the community, federated learning community, has been studying, such as local training and server updates and so on in this algorithm. So the future of training of large language models definitely is distributed, federated, or collaborative, whatever you want to call it. National AI Research and Development Strategic Plan, which I don't know, actually something that the US wants to invest in, given the recent events. But at least a couple of years ago, when this was produced, mentioned fair learning right in the strategy one, which further underscores the importance of this topic. Okay, so the final slide of this introductory part is on some of the topics or issues that are related to fair learning, such as communication complexity, data heterogeneity, device heterogeneity, privacy. So these are not all, these are just some 4 clusters of issues. And one can think about all of them. And in various papers, various researchers are focusing on 1, 2, 3 of them, and so on and so forth. I want to focus on one, but we'll see that this at some point gets connected with communication compression as well, with variance reduction as well, and so on and so forth. But the main idea is asynchronicity, and we'll be asking the question, is this the right way of handling device heterogeneity? What type of device heterogeneity, and how should we adjust the current algorithms in order to make them perform better in theory? Okay, so now a technical introduction to the problem. So we want to solve the classical finite sum minimization problem. I now see that Artur said the photo was taken a little over a year ago. Okay, thank you. You could have just, I don't think I'll have time to be looking through the chat, so Samuel might tell me what one can find in there, or if you can unmute yourself somehow and just tell me directly, I would appreciate it.
Yeah, I'll be monitoring the chat, so no need for you to check it.
And there's another talk on asynchronous FL. Okay, I see. Good. All right, so this is a very standard formulation of the problem. We want to minimize average of a bunch of functions, where n is the number of machines, d is the number of parameters, and these functions are some local loss functions over the local data. Now, typically people will think of weighted average, and these weights have something to do with how many data points you have on each client, but this is completely equivalent formulation. You can just hide the weights inside the definition of the functions FIs, which is what I'm doing here. Okay, so how does, well, this is completely standard. How does this setup differ from the classical setup? It's right here. We're now going to assume that it takes a certain amount of time in seconds for each client or worker or device to compute stochastic gradient of their own local loss function. So in this case, we tau I seconds for worker I to compute a stochastic gradient. And these times will be ordered from the smallest to the largest. So the first worker is the fastest worker, the second is the second fastest, and so on. And of course, no worker takes 0 seconds, because if that happens, you have an infinitely fast worker, and then you can do magic with such a worker, and we want to avoid that. We will also assume at some points that it takes a certain amount of time, theta I seconds, for worker I to communicate a d-dimensional vector to the server. So we'll start thinking about this once we introduce communication into the picture. But in the beginning, we'll just assume that this theta I is just 0. So we'll assume infinitely fast communication. We'll purely focus on the computation times, tau i's. And later on, in some extension, we'll throw in the theta i's and see whether we can still do something interesting in that more complicated and more realistic setup as well. And our goal is to find an approximate stationary point. So this is classical. We'll be assuming lower bounded functions and L smoothness throughout. And we want to just find a possibly random vector, because the algorithm is going to be randomized such that this expected squared norm of the gradient is below epsilon. Okay, so far so good. This is the setup. If you have any questions, please raise your hand, shout. Samuel will unmute you, and I'm happy to answer any questions. So let's try to think together first of some algorithms that could be designed to solve this problem under these computation times or computation constraints. So let's say we have just 3 workers. We have a server. These workers have to communicate through this server. And the server first sends the full model parameters to all the workers. Now, in this moment, imagine this is infinitely fast. We're not really worried about the communication cost at this moment, even though, of course, in reality, you have to worry about this. The reason why I'm not worried about communication times at first is because I really want to think about what happens, what should be the right algorithm if the computation times are arbitrarily heterogeneous, even if communication times were 0. And it turns out we don't have theoretical answer to that question. So you want to first handle simpler question before handling a harder question. So this simplification is not here because we think this is a realistic scenario. It's just necessity. If we don't know how to answer a simpler question, maybe we should first answer a simpler question if we want to understand what's going on theoretically. So then everybody, all these 3 workers compute stochastic gradients. And now remember, tau1 was the smallest number. So the first worker does this first, the second worker finishes second, and the third worker finishes third. And now let's say we're going to wait for all of these 3 workers. The method will not be asynchronous, and all of them will send stochastic gradient back to the server. The server averages and takes 1 mini-batch SGD step with mini-batch size 3. And now I want people to be unmuted because I want to have a little bit of a discussion with the audience about whether this algorithm seems reasonable or not. So let's just try to criticize this algorithm in this setup and try to think what we could possibly do to make it better. So I'll pause here, and I'm welcoming any suggestions about, is this a good algorithm in this setup with this infinitely fast communication, but arbitrarily heterogeneous computation, or not? So again, this is just mini-batch SGD with mini-batch size 3. Is this the right thing to do or not?
So anybody can unmute themselves now. So Phil, if you want to add to the discussion.
So the answer is, for me, it's no.
And can you say why?
Yes, I have to say that I worked on a related problem, so this is why I think that I know the answer. But if we have a lot of like fast worker and we only have one slow worker, and even like if his dataset is not that great, everyone is going to wait for him.
Right. So is it always a bad algorithm, or it could sometimes be good? Does it depend on the compute times?
I would say that
here.
Oh, that's a good question. I would say that if everyone, let's take the extreme case, that everyone has exactly the same compute time, then I would say that probably it will be a good one, but I haven't thought about it deeply.
Yeah, so that sounds reasonable. Yeah, so this sounds reasonable. So if the compute times are roughly the same, maybe this is a good algorithm because nobody's waiting for anybody. And since communication is infinitely fast, and maybe let's say the aggregation at a server is infinitely fast as a abstraction, then there doesn't seem to be any delay, any lost time, any idleness in the system. So at least from that perspective, it seems quite okay. However, what if tau3 is, let's say, 1 year, tau1 is 1 second, and tau2 is 1 day? So as soon as you think about these kinds of extremes, then it's very clear we shouldn't be waiting for 1 year for one stochastic gradient from the third worker. So then it seems to be very, very strange algorithm. Seems to be another comment in the chat. Yeah, so please, if you could unmute yourself and just say something, because I won't be looking into the chat. I just want to talk to people instead of reading messages. So what would you suggest as an alternative to this algorithm? I'm asking everybody, in the case when tau3 is much larger or tau2 much larger than tau1. So these times are quite different. What should we do instead? Or what could we do instead?
For me, it's like what you said, like go for an asynchronous algorithm.
Okay, so that's one solution. I will talk about this at some point. Now, so one thing that seems to make sense is if tau 3 is really, really huge, maybe it could be even infinite. We don't even have to assume that this is finite. It could be infinite. If it's infinite, this means that this machine just crashed. It's not working, right? It's not responsive. So then we shouldn't worry about the machine at all, and we should just be training using the other two machines. And if it's not infinite, but finite and very large, then an asynchronous method, I'll describe what I mean by this later, but for those of you who know, would still need to apply the stochastic gradient once to the model once it arrives, even if it arrives after a year. Maybe with a smaller step size, maybe, but it will still be applied, but it looks very counterintuitive, right? If already you're training for a year, you've done maybe tens of thousands, millions of iterations, and at some point comes stochastic gradient at x0, which is totally outdated model. Maybe you just shouldn't apply it. Okay. And by the way, this is something that asynchronous methods don't do. They don't do this. They treat everybody from the perspective that their updates are useful. They would not suppress updates from any of the workers. And this already points towards the idea that maybe what asynchronous methods do is not exactly right. That maybe some workers, in some instances, in some cases, should be ignored and shouldn't be allowed to contribute. Okay, so let's move on from this a little bit. So I'll talk about three types of heterogeneity in this talk: data, compute, and communication. And I want you to be aware of this. And I will not always assume that all of these three data heterogeneity assumptions are satisfied. In other words, I will not always allow data, compute, and communication heterogeneity. In fact, in the first part of the talk, which is the main part of the talk, I will assume that the data is homogeneous. I will assume that the communication times are zero, so thetas are zero, and the main difficulty and the only difficulty will come from the arbitrarily different compute times. Now, again, I want to stress that this is not because I think this is realistic. Obviously, it's not. In fairy learning, the data is not homogeneous, actually very, very heterogeneous. And there's all kinds of other types of heterogeneity. But as I said, if we don't understand what to do, what is the right thing to do, or what is the optimal algorithm, even in this regime, then it's very difficult to think of more complicated regimes. So we'll think of this regime first, and then we try to lift the homogeneity assumptions for data and communication, come up with an algorithm which can handle all of these three types of data heterogeneity in an optimal way. Okay, so we'll assume that the function we want to minimize actually is lower bounded, so that there would be a stationary point with a small of the type that we want to find, so point with small gradient norm. And we're going to assume that the stochastic gradients are unbiased and have variance bounded by some constant sigma square. And we're going to assume that the Lipschitz constants of those individual loss functions on the clients are all bounded by some constant L. We could possibly allow different constants for different clients or different stochastic, different variances for different clients, but we're not going to do that here for simplification. So you'll see L and sigma around. Okay, so we've written several papers on this topic. These are the first 5, and we have written, I believe, 2 more. I'll mention them a little bit later. You can't read the titles, but it all started with this first paper, and I'll really talk about the first paper first. But I want to give you a very high-level idea what these papers contain before we even start talking about them. So the first paper from roughly 2 years ago introduces 3 algorithms: Rennala SGD, Millenia SGD, and accelerated Rennala SGD. And here for Rennala SGD, we assume that in all of these algorithms, we assume that the communication times are 0. So there's no issue with communication. And we assume in Rennala SGD that the computation times are arbitrarily different. However, the data is homogeneous. And in Millenia SGD, we leave the data homogeneity assumption. And I don't want to worry now about this accelerated Rennala SGD for the moment, because that's in the convex case. However, Rennala and Millenia are analyzing the non-convex case. And these algorithms are optimal, and they are semi-asynchronous. So it turns out that they have some asynchronous elements, but they also have some synchronous elements. And at that moment in time, 2 years ago, it was surprising that an optimal algorithm was not what people were developing in the asynchronous SGD community. It was something new. And the upper bound was better than the best known upper bounds, and they matched newly developed lower bounds. So then in the second paper, roughly a year later, we started to think about the situation where the communication times are also, first of all, non-zero, but also arbitrarily different. So we kept the computation times arbitrarily heterogeneous, and we added arbitrary heterogeneity of the communication times. However, in this case, we had to drop the data heterogeneity assumption, the data heterogeneity which we could cater to in Millenia SGD, but in this case for Shadowheart SGD we couldn't. So we have two sources of heterogeneity, which is communication and computation heterogeneity, but we have data homogeneity in this regime. Okay, so I'll have a couple slides on Shadowheart SGD in this talk too. So then we asked the question, what happens if we know that all of these loss functions on the clients are of a finite sum form? Before we just assume we have unbiased estimate of the gradient with the bounded variance, but we don't necessarily assume finite sum. Once you have finite sum structure, you could use variance reduction to improve the upper bound. So we know that finite sum structure allows for this trick to be used. So we're wondering if we can design better asynchronous methods, and the answer was positive, and we could also prove matching lower bounds in a certain regime, and the regime is if each client contains a large enough number of data points larger than the square of the number of clients. So that's the large scale regime. Okay, so then we ask the question, can we do all of this on a graph in a decentralized fashion? So now there wouldn't be one centralized server, but there would be a connected graph. The nodes would be the devices, and the links would be communication links. And in this paper, we lifted all the homogeneity assumptions, so everything could be heterogeneous: computation, communication, and also data. So there's several more papers, more recent ones. So one is Mindflayer SGD by Arto, who's in the audience, and I don't know whether Omar is in the audience or not. So here we looked at the random compute times setup and have some algorithm that can outperform the previously designed optimal algorithm in this regime. And this is not a surprise, because the previous algorithm, such as Rennala SGD, was really designed for deterministic compute times, not for random compute times. So it's clear that maybe there's not exactly the right algorithm for random compute times. However, one can adjust this method to be optimal also in that regime, and there is extra work by Sasha Turin, which is not listed here, where he managed to do so. And now from this year, there's Ringmaster ASGD. This is actually the first method which is fully asynchronous, and it's optimal. The previous methods, they are all partially asynchronous and partially synchronous, but this one is fully asynchronous. And then we have the adaptive task allocation algorithm, which tries to learn something adaptively throughout the iterative process. But I will not have time to talk about any of these papers on this slide. In fact, I won't have time to talk about most of the stuff even on this slide, but some of it I'll cover. Okay, so I want to stop now in case anybody has any high-level questions about these papers and what they contain. Does it make sense? Do you want to ask anything, or should I continue? So in any case, if you have any questions, please just unmute yourself and shout. You don't have to wait for me to prompt you to ask anything. So I have not been really covering anything technical so far, so I guess this is all still fine. Now you might be wondering what these algorithm names mean. Well, they're all some characters from computer games. Now, I'm not a game player, but somebody on the team is. So I'm not going to name that person, but so now we somehow stopped using girlfriends and wives' names for algorithms and started this new trend of using computer games. So if you're designing a new asynchronous SGD method, now I think it's there's a law that you have to use some computer game for this. So please follow this tradition. Thank you very much. Okay, so here's another high-level point of view of those first 5 papers. And after this, we'll really start talking about the first algorithm. And this could be useful to those of you who maybe want to start working on this in this area, but don't quite know what was done and what was not done. So as I mentioned, all of these papers cater to compute heterogeneity. So if you look at the second column, you have green check marks. That's the one fixed thing which we want to really consider in all of those algorithms. However, data heterogeneity is assumed only in Millenia SGD algorithm and this Amelie SGD in the decentralized setup. So in most of these algorithms, we had to assume we're in the data homogeneous regime. And even though we assumed that we had a difficult time designing these methods and proving optimality. Now, communication heterogeneity is assumed in 3 of these, Shadowheart SGD and then Fragile and Amelie SGD. And in 2 of these, in this, let's say 5 other algorithms, we just assume that not only there's no communication heterogeneity, but communication is infinitely fast. So the communication cost is just 0. Almost everywhere we assume the smooth non-convex regime, and only in one algorithm, the accelerated Rennala SGD, we assume the smooth convex regime. And everything is centralized except for the last algorithm where we work on a graph and we get optimal time complexity almost in every case, but not exactly in every case. I mean, on purpose, this FRA SGD algorithm, we knew this would be suboptimal, but we wanted to think about it and analyze it anyway. Okay. So maybe this is a good time to pause for a moment and for you to ask anything, and then we'll start thinking about how to design Rennala SGD.
I have a question. It's a bit off topic, but do you think that now that you can control like the computation heterogeneity and also the communication, it can open the way to analyzing or designing better how many rounds, like the heterogeneous number of rounds that each worker can take?
I'm not sure I understood the question, to be honest. So you want, I'm not sure I understood. You would need to rephrase it.
Yeah, in a way, I want to adjust the number of runs that I take to my computational complex, or how well my hardware is, and also try to like get away from the assumption that everyone takes the same number of runs.
Well, that assumption actually is not here in these algorithms. So in some of these methods, this is not happening. So that assumption is not made in the design of these algorithms.
Okay, thank you.
Okay. Any other question? There's something in the chat.
Maybe a small follow-up question.
Yeah.
Do you consider multiple local steps in the algorithms, like in federated averaging?
No. So there's one answer to this. One answer could be no, and the other answer could be that in fact, these as the stochastic gradients computed by these different machines, and the fact that each machine will eventually compute different number of stochastic gradients could be seen as some sort of local training Not the classical one, because the model is maybe not immediately updated, at least in the semi-asynchronous methods. But for Ringmaster SGD, this could be certainly thought of as local steps, but local steps of a very different nature. So local steps, the classical local steps make sense even in the regime where all the clients are equally fast. Even then, one can show through methods such as proskip, and then the methods that were inspired by proskip, such as renprox and so on, 5GCS, etc., that the local steps could accelerate in the strongly convex and L-smooth regime. They could accelerate communication complexity. So this is one thing that local steps can do. But one can think of these stochastic gradients in this asynchronous setup as a different type of local steps, which do something else. And what they do is they don't accelerate in terms of moving from condition number to square root of condition number, but they accelerate the training due to device heterogeneity, compute or communication heterogeneity. So it's just a very different type of acceleration.
Yeah, thank you for the detailed answer.
But are you satisfied with the answer, Eduard? You thank me, but maybe you thank me and you are not happy.
Yeah, I'm happy. I'm satisfied.
Thanks for lying. Good. Okay. So there's a question by Ali. Can you ask this in person?
Okay, so can you hear me now?
Yes.
So in the case of computation heterogeneity, does it make sense to weight the updates by a function that decays exponentially with time? So the later they come, the less they matter, something like that.
Yeah. So in fact, some recent papers before our line of work did suggest that maybe this is one way how you should handle large delays and slow workers, but it's not the optimal way. It turns out you should do something more dramatic. And so, for instance, in Ringmaster SGD, we showed that you should have some kind of threshold for delay, and beyond some delay, you just shouldn't consider workers at all. So it's not exponential, but there's just threshold. Up to the threshold, you accept everybody. After the threshold, nobody. And that turns out to be theoretically optimal.
Okay, so at some point we ignore them totally, right?
Yes, yes.
And
this is one of the insights of this line of work, that not everybody is going to be useful. And this is what everybody knows from their own lives outside of the life of algorithms. So if you form a team in a company or in a research lab or anywhere, and if you just hire somebody who really shouldn't have been hired, and they just, I don't know, watch Twitter all day long, or watch YouTube videos, play games, and don't do any work, then maybe they shouldn't contribute to the project at all. You shouldn't weight them with some exponentially small contribution. They should just be fired, right? I mean, some people can actively damage team. And it's the same thing in case of algorithms and parallel SGD. Some workers were just so slow that it's just better to tell them, go home, do something else. You're not going to help us.
Thank you for the answer.
Okay, so now I'll move on and let's look at our first algorithm. This is not our algorithm that we propose, but I want us to jointly think about how to handle this compute heterogeneity and start to think about possible solutions to the problem and criticizing each solution, which will lead us step by step to the correct solution. So let's say we have 3 workers, and the first worker is the fastest, so that's why the green rectangle is the shortest. The second computer, which is, well, at the bottom, is the second fastest, and the third worker, the phone, is the slowest one. And the Hero SGD method follows the idea, let's ask the fastest worker do all the job. In fact, this may remind you of some team dynamics in various settings. Very often, you just ask the fastest guy to do it all, and everybody else goes on vacation. This is not entirely unreasonable algorithm. So can you can you think about this a little bit and tell me why this actually might be a reasonable algorithm? And I claim that sometimes it's actually a good idea to run hero SGD rather than, let's say, mini batch SGD, which is the method that we've seen at the beginning. When would that be the case? And anybody, please just unmute yourselves and shout.
If
I know it's
all,
yeah.
yeah, for example, if all other clients are very slow, like extremely slow,
Exactly.
then
Exactly. Yeah. Yeah. So if tau2 is a year, tau3 is a year, and tau1 is a second, then of course the first worker should do it all because it will be done training before the other workers even contribute one stochastic gradient. So, and we're trying to design an algorithm. Remember, we're trying to design an algorithm which is optimal for all configurations of what these values, these times, tau1, tau2, and tau3 could be. So we cannot exclude any theoretical possibility. We're not constrained here by assuming that all of these are approximately the same because maybe in industrial practice, these are approximately the same. No, we want tau1, tau2, tau3 to be absolutely anything, even such a huge difference, such as a year to a second. So this seems like the right algorithm in the regime when tau2 and tau3 are really, really large. And notice this is neither asynchronous SGD, which if you know what that is, you know that this is not it. And if you don't know what it is, doesn't matter. You can kind of intuit it's not asynchronous SGD, and it's not mini-batch SGD. This is just hero SGD. Okay. On the other hand, it's definitely not a good idea to do this if, let's say, tau1 is equal to tau2 is equal to tau3, because then you can get 3 stochastic gradients at the same time as 1 stochastic gradient. So maybe then you should do mini-batch SGD, which with mini-batch size 3. Okay, so let's move on and let's do this mini-batch SGD, which I just mentioned. So now the idea would be each worker computes 1 stochastic gradient. We wait for everybody. Average those 3 stochastic gradients, take the step. So this is the algorithm that we started with. And we already criticized it. If tau3 is a year and tau1 is a second and tau2 is a minute, we definitely shouldn't wait for the third worker. On the other hand, if these 3 times are roughly the same, maybe this little idle time right here, I don't know whether you can see my mouse, and here, maybe there's not a big problem for the performance of the algorithm. But if this idle time becomes really, really large for any of the workers or many of these workers, this will seem like an algorithm not well designed. So again, mini-batch SGD could be a good method, could even be possibly the optimal method, but this really depends on the exact values of tau1, tau2, and tau3. Let's look yet at another method. So this is asynchronous SGD method. And for those of you who never seen this before, I will try to explain it through this idea that all workers are slaves and useful. So let's say you want to design an algorithm and you want to follow this philosophy that every worker is useful and every worker is a slave. So what do you mean by slave? That there shouldn't be any idle time for anybody. Everybody should be just working. Here, clearly, not everybody is slave, only the third worker is slave, but the first and second worker, they have some idle time. So this is definitely not going to be asynchronous SGD. And here, second and third worker have idle time the whole time. So these are probably some managers or something. So here, everybody is a slave, everybody's working at all times, and they are useful, which means we have to include their outputs to the algorithm. So we cannot just discount somebody and say you are not going to, your stochastic gradient will not be used. So how would such an algorithm be designed? So we ask all these 3 workers to compute stochastic gradient at x0. Now they start computing, and the first one, the fastest one, the green one, is finishes first. And as soon as the first one finishes, the stochastic gradient is applied to the model, and we have a new model x1. As soon as we have model x1, we ask the same worker to compute stochastic gradient at x1, and it starts computing. Then at this time x2, we get the stochastic gradient, which was computed at x0 from the second worker. That happens right here. And the stochastic gradient is now applied, but not to model x0, but to model x1, because that's the latest model. So already here we see a very strange iteration where x2 is equal to x1 minus a learning rate times the stochastic gradient at x0. So you can see that the method looks very strange because there is a disconnect between the current model and the model at which the stochastic gradient, which is being used as an update, was computed. And this thing just continues like this in this very chaotic way. And again, if tau3 is really large number, then it can happen that at some point, maybe x 10 million, we're going to subtract with some learning rate stochastic gradient computed at 0. So that sounds like a very strange algorithm. But this is what asynchronous SGD is. And this has been the dominant paradigm for tackling compute heterogeneity in parallel settings or distributed settings, or let's say in federated learning. However, what I want to criticize here is this algorithmic idea behind the construction of the algorithm. The algorithmic idea is everybody is useful and everybody is a slave. And because of it, because people have been following this algorithmic idea very strongly, an optimal method was not designed. It turns out that not everybody is useful. And this is what, in fact, you can intuit already by thinking of the set situation where tau3 is really, really huge, then that worker shouldn't really be useful. But nevertheless, asynchronous SGD, as analyzed, assumed that everybody is useful. And this is how people done the theory. Okay, so let me pause here. Any questions that you might have about these three methods: Hero SGD, fair mini-batch SGD, and asynchronous SGD? Does it make sense? Is everybody happy?
Maybe a small question regarding the setting. Do we assume that numbers tau1, tau2, and tau3 are known to the server or to everybody?
So at this stage of the talk, I'm just assuming that they are known and fixed. However, in most of these papers, we also have variants of these algorithms where this is not assumed. And we have variants which are adaptive to these values and which work even if these values are not only not known, but can vary throughout the process in various ways. And the algorithm will still work even if these taus vary and change, even if they're random in some cases and so on.
But still, like, okay, yeah. It's fine. Thank you.
Yeah, so we kind of answer this question by layering. So we first start with the simplified setting where we say, okay, let's assume these are known and let's see what we would do. And then we say, okay, but in practice, maybe you don't know these values. So what happens if they're still fixed, but you don't know them? Then we modify the algorithm and have almost the same complexity. And then we may ask even further question, what if they can even vary? They're not only not known and fixed, but they could even vary. Then we have yet another answer to what one can do. And sometimes the third answer and second answer is the same. But I will not actually have time to talk about that. I just don't have time to get to that level of depth. But I can maybe comment on this or point you to the right source.
Yeah, thank you. It's fine.
Okay, so now let's look at our method. But before this, I want to pay homage to this very influential paper, Hogwild, which I read back then when this was produced in 2011. I was at the conference it was, I think, Foundations of Computational Mathematics conference in Budapest, and I've seen a talk by, I don't know, probably Ben Recht gave the talk then, I don't quite remember, on the Hogwild algorithm. It got NeurIPS 2020 Test of Time Award, very influential. So this is how asynchronicity somehow got into NeurIPS, into the AI community, even though, of course, asynchronous iterations have been considered in optimization literature for several decades before this, but not in connection with stochasticity as far as I know. And the inspiration for our work are these two beautiful papers, one by KAUST, Yamishenko, Francis Bach, Matthew Even, and Blake Woodward from Paris, and the other one by Nastya Koloskova, Sebastian Stich, and Martin Yagi from EPFL. You can see that they were posted on arXiv basically on the same day, June 15, June 16. So this is one of those cases in history where people discover almost the same thing at the same time. And these papers are really very nice. And they are so nice that, in fact, I was not interested in asynchronous optimization before this. I only observed the field, and I was unhappy with how the results were presented and what assumptions were made in these algorithms. And I just couldn't believe these complex results that they were obtaining. And there is some reason behind this. And the reason really is that the first citizen quantity in those papers before these two papers were not these computation times, but they were delays. So people made assumptions that let's assume that we run the algorithm and the maximum delay is this, or average delays is this, or something of that type. And the delay is the number of iterations between when the model was updated and when the stochastic gradient was computed. And the problem with this is that this is a property of the algorithm. So you cannot assume something about the algorithm. And this is not really the first citizen. The first citizen here are the compute times. That's the input. That's where the device heterogeneity comes in. And maybe if delays then happen throughout the algorithm, they should be function of these computation times, but one shouldn't start with assuming what the delays are. So then once you got some iteration complexity results, they were simply just hard to interpret because you couldn't understand how they mapped onto a notion of time. How much time does it take for the algorithm to solve the problem? So these papers could actually then, for the first time, really think about a notion of time complexity because the iteration complexity times here really made sense, and you could multiply the number of iterations by some quantity, which then the product then really corresponded to some measure of time in which the algorithm runs. So the proofs were quite fundamentally different and also much more meaningful. So what these people did, they basically proved that asynchronous SGD, as described previously, is better than mini-batch SGD. And that this is a beautiful result. And what we really ask in this Rennala SGD paper is that the end of the story, or can asynchronous SGD be further improved? So now we are here in this first algorithm, and I will explain to you what Rennala SGD is. So what Rennala SGD is this algorithm. It's basically mini-batch SGD with a certain mini-batch size. So in this case, it'd be, let's say, 4. I'm just imagining it's 4. So we wait for 2 stochastic gradients from the fastest worker, 1 stochastic gradient from the second slowest, and 1 stochastic gradient from the slowest worker. Then at this time x1, we average these 4 stochastic gradients, take mini-batch SGD step with mini-batch size 4, and we repeat the process. So we kind of kill these processes here. We kill this thing as this thing, and we restart everything. Now, it turns out that this mini-batch size, in this case 4, does not depend at all on these compute times, tau1, tau2, and tau3. It only depends on the variance of the stochastic gradient and the epsilon in the accuracy threshold, epsilon. So that's all, just on these 2 quantities. So there's a certain formula that you can form by combining sigma squared and epsilon to get the optimal image size. Now this method, notice that is half synchronous and half asynchronous. So it's synchronous in the sense that when we update the model from x0 to x1, it's 1 synchronous mini-batch SGD step. Okay, so everything is synchronous there. However, the collection of the mini-batch is asynchronous. So nobody has to wait for anybody in order to proceed computing these stochastic gradients, right? So once the first worker is done with the first stochastic gradient, it immediately starts computing the second stochastic gradient, completely disregarding what are the other computers doing. So it's, again, synchronous iteration with asynchronous collection of the mini-batch size. So this is run on SGD, and it turns out this very, very simple strategy is optimal. So this will give you optimal time complexity. Okay, so I'll stop in maybe 2 more slides, roughly. So here's the upper bound. The upper bound that we prove works like this. That we have m, which is some kind of a dummy variable between 1 and n is the number of machines. and you have to minimize this expression, this product in M. Then you have the compute times here. So this is basically harmonic mean of the M fastest compute times. We have the smoothness constant that you've seen at the beginning. We have some kind of functional suboptimality. We have the variance of the stochastic gradients, and we have the accuracy or error tolerance epsilon. And we have this constant 96 in front of everything. So one way how you can think of this M is if you compute this minimum, let's say you know all of these tau i's, you know L, you know sigma, let's say you know all of these quantities. In practice, you may not know them, but let's say you know them. And when you do the minimization over M, and the result is 1, then you should think that maybe in this case, the hero SGD method is the optimal method, because this M will then tell you only the fastest worker should be working. If M is going to be N, the way you should think of this is that mini-batch SGD, where everybody contributes, should be the optimal method. So mini-batch SGD could be optimal. Hero SGD could also be optimal. And if M is strictly larger than 1 and strictly smaller than N, then our method, Rennala SGD, will strictly ignore some workers because they're just too slow. So all of those methods that I mentioned at the beginning, I mentioned on purpose because they all are good methods in some regime, and our Rennala SGD method basically recovers them in special case. Now, this complexity wouldn't be all that interesting if we didn't have this matching lower bound. And because we have a matching lower bound, then we can say that Rennala SGD is optimal. And it turns out this is the first optimal parallel SGD method. So all other SGD methods which work in parallel have worse upper bound, and this lower bound is new. So I'll stop here, and I encourage any questions you may have.
I have a question about the M. So you assume that it is fixed around like throughout your algorithm, right?
No. So this
Okay.
M here, the way you should think of this is complexity result. So in the algorithm, you don't work with M in the algorithm.
Okay, you work with
in the algorithm, what you work with is certain mini-batch size. And let's say in this case it's 4. And if and the server is waiting for 4 stochastic gradients.
Okay. So
and if it gets them just from the first worker, then that means the method will be hero SGD and it will ignore everybody else. If it gets 1 from everybody, then the mini-batch size would be 3, and this would be just standard mini-batch SGD. So really the parameter here is the mini-batch size, and the server just waits for stochastic gradients, for a certain number of stochastic gradients. So this doesn't mean that M is necessarily fixed. But if the compute times are really fixed and they never changed, then in fact the number of contributing workers, which is going to be M, will be fixed throughout.
Yeah, and have you tried like an adaptive choice of like the number of mini-batch or number of stochastic gradients you want for the calculation of the mini-batch?
So so there's 2 answers to this. First answer is that it doesn't make sense in the sense that this method already is optimal, so we cannot improve it. Since we have a matching lower bound, we cannot improve it. So if we tried something adaptive, then what could be the reason for it? Well, maybe the reason could be that it could be better in practice slightly, but definitely only by at most some constant factors, but it wouldn't be able to be the lower bound. But there is a deeper way one can interpret your question, which is probably what you meant, which is what happens if maybe even the times keep changing. So maybe the tau 1, tau 2, tau 3 are not fixed, but they keep changing. And at some point, maybe some machine just crashes so that the time becomes infinite for a while, then it becomes finite again, and so on and so forth. Well, maybe in the regime, it might make sense to do something different. But at this point, I'm not talking about the regime where the times are changing. But we do have a versions of these methods, even considering the scenario that I mentioned, that these times can be arbitrarily different. And then at least we get adaptivity to the compute times that we don't need to know, and they can be varying.
Yeah, my motivation was more like from the sense that at least in the beginning, maybe I don't care specifically about like very much about like the precision of the gradient. And also if I have like diminishing step size maybe later on that the weights are very small, I don't care that much again about the variance if it's sufficiently small.
Yes. So here we have a fixed step size rule, and it turns out in the say the smooth non-convex regime that's enough.
Mhm.
And and um, and you're right in the following, that the mini-batch size is a function of the variance of the stochastic gradient and of epsilon. So you need to know these two things if you want to choose the mini-batch size to run the algorithm. And if you don't know the epsilon, maybe you want to have some adaptivity to the epsilon itself. And to the best of my knowledge, that is still an open problem. So if you want to have a method where you will decide on the fly what accuracy you want, or you want any accuracy and not some prescribed accuracy, adaptivity to that, we don't have.
Okay, thank you.
And then it would indeed make sense to even change M.
Okay.
And with a student of mine roughly a year ago, we looked at this briefly and we've run some experiments and we have some, let's say, heuristic way of doing it, which seems to work. But we don't have a theory which is sufficiently good for us to publish this. So we thought about this for a while. So I certainly appreciate the question and understand that this is a completely valid point.
Okay, thanks.
Okay. Any other
Sorry, I
question?
have a question. Yes.
Don't apologize. I like questions. So no, don't say sorry, but say, I have a
Okay.
question for you, and I'll be happy.
Okay. So wouldn't that introduce somewhat of a bias? So say when a machine is much faster than the others, wouldn't we be biased towards the gradients coming from that one machine? And do we need to handle this in some way?
So this is excellent question. And here I want to just remind everybody that in this case, we are in this Rennala SGD case. Notice that we work with data homogeneous regime. So I'm assuming all the functions are the same, which means these are stochastic gradients of the same loss function, which means there's no bias, doesn't matter. These are all stochastic gradients of the total objective function. But if these functions were different, if you had data heterogeneity, then absolutely you cannot exclude even the slowest worker from the algorithm. That's what in Millenia SGD will be the case. Because then some worker can contain some part of problem description, which is needed for you to solve the problem. So if you ignore that worker, you can never solve the problem.
So is this an active area? So our people are working on it currently to handle this problem?
Well, it's not that they, send me emails and let me know whether they work on it or not. So I do not know who is working on what, but it's certainly something that we're thinking about. And we thought about this in this Millenia SGD paper and this Amelie, where we assume where we allow for heterogeneity. So ideally, we want to allow for all kinds of heterogeneity. So I would say it must be active area of research, but since all of this is very new and started roughly 2 years ago, with these optimal algorithms, before we had these suboptimal asynchronous algorithms, now we have optimal ones, then I would say maybe not many people know about these works yet, so not many people probably work on it yet.
Very insightful. Thank you so much.
Good. So please keep interrupting me at any time. Don't wait for me. Okay. So we have this matching lower bound. Everything is good and nice. Now, just to mention something from the background of the theoretical approach to this. So classically, one works with this classical Oracle protocol. I'm not going to go through this in details, but you have some function class, Oracle class, and algorithm class, and this distribution covers the noise of the stochastic gradients, and you ask the Oracle to give you stochastic gradient at some point with some seed, with some randomness. It will output the stochastic gradient, and then you throw the stochastic gradient into this algorithm AK, and it will update the model. And if you have a single worker, then this oracle makes sense, because when you run this oracle, every time you run it, it will take a fixed amount of time. So the number of iterations is a good proxy for the time complexity, because you can just multiply the number of iterations by some constant, and that constant is going to be the time it takes for one iteration to take place, and then number of iterations is a good proxy for time complexity. However, for parallel methods, this is not the case, and certainly for methods such as asynchronous SGD. So if you look at methods such as this, let's look at how this asynchronous SGD look like. Is this crazy kind of pattern? Then if you take, let's say, 25, or let's take 5 iterations of this, how much time does it take? So it's not so easy to figure out exactly how much time does it take for this if you have 5 iterations. So let's therefore introduce, so in this classical oracle, what we work with is we just count the minimal number of iterations for this for finding an epsilon accurate solution, and we do this in the worst case over all the functions and over all the for the oracle class, and the best case over the algorithm. However, this is only meaningful, and that's the claim that we make in the paper. This is meaningful for sequential methods, where the number of iterations really is a proxy for the total work. However, in the parallel setup, what we have to introduce is extra parameters into the oracle, which keep track of time. So when you ask now this oracle to compute stochastic gradient at iteration xk with some randomness zeta k plus 1, then the oracle has some state sk. It kind of remembers something, and it will it will update its state, and this happens at a certain time. And the oracle needs to remember the time, and it has to update the state. So basically, these oracles behave as natural computers, which keep track of when they were asked to do something, how much it took, and they would just update their own internal clock. And in this way, once you have this kind of an oracle which can update the internal clock, and I don't have time to explain how this really works. This the technicality of it will take longer, but if you just think of internal clock, I think that's pretty good enough analogy for this. Then what you have to do, you have to now take the infimum over the time, not over the iterations, and then now the time is remembered by this oracle, so that there is some iterate in that amount of time for which you have solved the problem to epsilon accuracy. So this is time complexity, and we express everything in time complexity. So the upper bound and the lower bound, the optimality is in terms of this notion of time complexity. Iteration complexity is simply not up to the task. Okay. So now let's compare the complexity that we obtained with the previous complexities. So the first one is mini-batch SGD. Notice that there's certain quantity here in these parentheses, which is multiplied by tau n. And remember that tau n is the time of the slowest worker. And we have to multiply by the time of the slowest worker because we are waiting for the slowest worker. So this is the number of iterations it would take for mini-batch SGD with mini-batch size n. That's why sigma squared is divided by n here. You can see that the variance scales linearly with the number of clients. This is the number of iterations it would take for mini-batch SGD with mini-batch size n to solve the problem. And each iteration takes tau n units of time because we wait for the slowest guy. So this is the time complexity. Now, Koloskova and Kotters, Mishenka and Kotters, they showed that this can be improved. And you can see that in the parentheses, you have exactly the same quantity as for mini-batch SGD. However, they replace the maximum of those compute times by harmonic mean of all the compute times. And since harmonic mean is definitely smaller than the maximum of any sequence of positive numbers, then this is strict, this is improvement. Well, not necessarily strict. If all the towers are the same, then it's the same. But unless that is the case, this is strict improvement over mini-batch SGD. And that's why the results were so beautiful and inspiring. And what we've done in Rennala SGD is went just one step further, where we say that, in fact, you shouldn't work with all the workers, you should work only with certain number of fastest workers. So there'll be the M, and then the variance gets divided by M. And here the harmonic mean will only work over the M fastest workers. And obviously, this upper bound cannot be worse than this upper bound of asynchronous SGD, simply because you can always, instead of minimizing over M from this set 1 through N, you can just choose M is equal to N. And if you choose M is equal to N, you get exactly the same bound. But the minimizer could be achieved at some other value, and then you get improvement. And the lower bound matches this. Okay, so I'll pause again in case there are any questions. So I just noticed that Sasha Turinos is also here in the audience. So please, you can correct me or add any information at any point as you feel.
No, I think everything is fine. Thank you.
Okay. Okay, good. So let's continue. So here are some experiments. So these are artificial experiments. You can see that toy experiments where the compute times are just set to be square root of I. So the ith fastest worker will take square root of I seconds to compute stochastic gradient. Of course, completely, utterly artificial, but there's no shame in that because such artificial toy experiments are beautifully scientific because you can set these taus to be whatever you want, and then you can simulate these asynchronous workers and see whether the theory has any predictive power. In this case, we work with 10,000 workers. We don't have access to 10,000 actual workers, so all of this is simulated. But you can see that in this regime of this quite large heterogeneity of compute times, Rennala SGD is massively better by several orders of magnitude than mini-batch SGD or asynchronous SGD. So this is not really the worst case. There could be some other situations or some other distributions of compute times where the gap could be larger, but also vice versa. For some distributions of compute times, asynchronous SGD or mini-batch SGD can do as well as Rennala SGD. You can even maybe throw Hero SGD into the mix and see whether it does well. In this scenario, it wouldn't do all that well. Okay, so this is kind of the end. However, this is the end for those of you who only have roughly an hour plus for this talk. So feel free to go about your day. And if there's any people who want to continue to listen for a few more minutes, I will be quite happy to talk about these two further extensions. And this may take, I don't know, 10 or 15 more minutes. So I'll just go along. And as I said, feel free to just go about your day in case you don't have more time. So we'll look first at the first extension, which is this second method from the first paper, Millenia SGD. And in this method, we lifted the data homogeneity assumption. So in this case, the distributions could be different, which means the functions could be arbitrarily different, which means we cannot ignore even the slowest worker. So stuff has to be handled. The algorithm has to be adjusted. And the way it's adjusted, one can see it in this while loop. And this while loop can only be exited if I'm not going to explain this in detail, but this while loop can only be exited if every worker contributes at least one stochastic gradient. And that implicitly means that everybody has to contribute, even the slowest worker, at least one stochastic gradient. And now the S is, again, the mini-batch size, which is used by the algorithm, and it's sigma square over epsilon. And for Rennala SGD was maximum of sigma square over epsilon and 1. And for Millenia SGD is maximum of sigma square over epsilon and n. So we have to use at least n stochastic gradients where n is the number of workers. So this is slight modification of the Rennala SGD algorithm. And again, this is an example of approach to research where you first simplify a problem, try to understand it more deeply. And then once you understand it, maybe this gives you inspiration towards what to do in the more complicated setup. In this case, setup where you have also data heterogeneity. And then it is just simpler to discover this algorithm than if you wanted to cater to compute and data heterogeneity right from the beginning. Maybe it'd be harder to guess what the algorithm should look like. Now, for this algorithm, we have an upper bound and a matching lower bound. So this is also optimal algorithm. So this is optimal algorithm under compute heterogeneity and data heterogeneity. And again, remember, we assume communication is infinitely cheap. It's zero. And if you compare this to mini-batch SGD, to the best competing method, which of course this complexity works even for if you had any heterogeneity. So Sasha, you raised your hand, you can just say something right away.
Yeah, I mean, one important also change there is that how these stochastic gradients are normalized. I mean,
So here?
Like
So
in
please,
line 14, line 14.
Please just say what you want to say.
No,
I can say it, okay, or you
no,
can
no,
say
in line 14, yes, we have to, like in Rennala SGD, we just sum everything and then we normalize by the total sum. But here it's important that we here we take sum of like mean of the means here. So we first normalize inside every worker and then we normalize it again to preserve unbiasedness.
Yes.
Yeah.
Yes. Yes. Good. So thanks for adding this detail. So now if you look at this upper bound, which is the same as the new lower bound, which we prove in the paper, you can see that it's better than the upper bound for mini-batch SGD. And the only reason is because here we have arithmetic mean of the compute times. If you replace this arithmetic mean of the compute times by the worst compute time, then these two bounds would be exactly the same. So mini-batch SGD would have exactly the same complexity as Millenia SGD. But arithmetic mean could be arbitrarily better. And because it could be arbitrarily better, this complexity can be a lot better than the complexity of mini-batch SGD, and it's definitely improvement, and it cannot be improved anymore. Okay, so this is extension 1. Extension 2 would be looking at the convex regime. I want to just very quickly jump through this because maybe I want to show you one slide on Shadowheart SGD rather than this accelerated method. So here we also have an upper bound and lower bound. Now I don't really want to go through these letters and so on, but just believe me that since the upper bound is the same as the lower bound, this is optimal and the results are better than the competing methods. But I want to instead look at this Shadowheart SGD, where we for the first time introduce communication heterogeneity. So the communication times are not zero. We have arbitrary compute heterogeneity, but unfortunately we have to still assume data homogeneity. So now we're in the second paper and we have arbitrary communication heterogeneity. Okay, so let's look at the algorithm, and I will basically finish with this slide. Maybe I'll show some plots, but I guess I'll just finish with this slide. So this is the algorithm. It may look a little bit complicated, but I'll explain what it means. So we update everything synchronously. So again, this is a method similar to Rennala in the sense that we wait for all the workers to do some work. And once we have enough stochastic gradients, we combine them in various ways to make a single synchronous update. But let's explain how we actually go through this. So the learning rate is just basically 1 over the smoothness constant. There is a certain notion of an equilibrium time, which at the moment, just imagine this is some magical number, T star, which can be computed from the compute times if you knew them, the communication times if you knew them, the variance, the epsilon, and omega is some sort of variance of compressors that are being used here, the CIG. But at the moment, just don't worry about this at all. Just imagine there is some magical positive quantity, equilibrium time. And let's say you know it. And if you know it, I'll describe how to set the hyperparameters of this method. So first what you do, each worker I is going to compute BI stochastic gradients. And BI is possibly different from every worker. How many? This magical quantity equilibrium time divided by tau I. What does it mean? If some worker is very, very fast, then tau I is very small. So BI is going to be very large. So fast workers will be computing more stochastic gradients than slow workers. Okay? Now, as soon as each worker computes these BI stochastic gradients, they are added up. Well, they can be added up online, and only then communication happens. But it happens with a twist. So this is already different from Rennala SGD, where communication is done as soon as every single stochastic gradient is computed. And this is done because we don't pay any price for this, because communication is infinitely fast. So as soon as we have one stochastic gradient, we can just send it. But here communication costs, so one has to be very careful about when to communicate and what to communicate. So again, worker I is computing BI stochastic gradients, adds them up, so it doesn't average them, adds them up, and then these stochastic gradients are compressed. The sum is compressed. And it's compressed using an unbiased compressor with variance bounded by omega times the norm of the input squared. So this is classical notion of unbiased compressor from the literature on communication efficient distributed methods. So this sum is compressed, and then the compressed sum is communicated to the server, and the server just stores it. And this whole process is repeated mi times. So that means as soon as this compressed sum is communicated to the server stores it, and again, the worker computes BI stochastic gradients, compresses the sum, sends it to the server, and this is done mi times. What is mi? Mi is now inversely proportional to the communication speed. So if theta I is very small, mi is going to be very large. What does theta I small mean? It means that the connection link between the server and the idle worker is very fast. If the connection link is fast, then mi is allowed to be very large, which means we can send many, many compressed sums. And this makes complete sense on an intuitive level. Once this is concluded, all of these compressed sums are added, and a weighted average is computed. And this kind of division by the sum is only done so that you preserve unbiasedness of the estimator as a stochastic gradient. However, the weights have to be special, and there's a complicated formula for the weights, which depends on the variance, sigma, on the epsilon, depends on the mi, bi, and also on the omega. So basically almost on everything that we've seen so far. Apart from that, the algorithm is simple. As I said, I will repeat. Every device computes first, device I computes BI stochastic gradients, then adds them up, compresses, sends to the worker, to the server. This is repeated mi times. And as soon as the server receives all of these messages, compressed messages from all the workers, it takes certain weighted average of them with some special weights. As soon as that happens, you get an optimal algorithm. So we have a matching lower bound and an upper bound. However, neither the upper bound nor the lower bound have explicit form. They have implicit form because of the generality of the setup. So the time complexity is actually this equilibrium time T star with some particular parameters times L times delta divided by epsilon. And the lower bound is the same. And in order to compare this to some time complexity, so some other competing methods such as mini-batch SGD or quantized SGD or even Rennala SGD or asynchronous SGD, we have to think of some particular scenarios. So for instance, here we consider scenarios where sigma square over epsilon is either 1,000 or million. So if you consider this scenario, plus here in the footnote, we have some comment on how we choose D. This is a million-dimensional model with 1,000 workers, and so these HIs are supposed to be actually theta i's. They're kind of uniformly distributed between 0.1 and 1, and these compute times are uniformly distributed between 0.1 and 1. So if we look at these three scenarios, you can see that for Shadowheart SGD, we set here the multiplier as 1. That is the baseline method, the optimal method. And for instance, Rennala SGD, in this regime, where this ratio sigma square epsilon is 1, is 100 times slower. Quantized SGD is 3 times slower, and mini-batch SGD is 1,000 times slower. If we look, let's say, at the last column, where the variance is proportionally, a million times larger than the epsilon, then mini-batch SGD is 10,000 times slower than our method, so is QSGD, but Rennala SGD is only 1.5 times slower than our method. So in all of these cases, these other competing methods are slower, sometimes by several orders of magnitude. So this is really all I want to say. And well, I did promise extra plots with some computations, but all that you need to notice in these plots is that our method, which is the green one, is either at the bottom or near the bottom in all of these cases, while the competing methods are sometimes matching the performance of Shadowheart SGD and sometimes much, much slower. And this really is a testament to the optimality of the method and its ability to adjust its time complexity to the problem parameters, such as the compute and communication times. So this is all I wanted to say. If there's any more questions you have, please ask me or Sasha or any of the other potential co-authors who are in the call. I didn't check.
Hi, Peter.
Hey,
I have a
Mario.
question.
Yes.
For the Millenia SGD,
Yes.
the improvement is on the stochastic term, right? So if you assume the clients compute full gradient, then there's no way that asynchronous methods can beat mini-batch SGD, or in this case, mini-batch gradient descent.
Yeah, so sigma would be 0, and then
Zero,
this
yeah.
is just not there at all. So then you have just gradient descent basically, and yeah, and you're not
I mean,
beating.
why? Yeah, why? But intuitively, mini-batch SGD is optimal in that case. Why asynchronous cannot improve upon?
So I will ask
Or-
Sasha to answer this question. Sasha, go ahead.
No, I
I mean,
mean,
of course, you
like,
have a lower bound, but I just probably wanted some intuition.
no, first of all, here it's like L is like global smoothness constant, right? Here. So,
Mhm.
I mean, like a non-convex setting, like, no, okay, so the idea in the lower bound would be to put all your information about one into one worker. Okay?
Mhm.
So, like in the construction, only one worker, let's say the first worker will contain, like, let's say the slowest worker only will contain information about your function f, right? And all other workers, they will just contain 0. So, and for this construction, you just need to wait for the slowest worker. That's the worst case scenario, when this worst work is when the slowest worker contains all information. Like, is it clear or?
Yeah, I mean, that's how you constructed the lower bound, basically.
Yeah, it's how constructed the deterministic part constructed. Yes, for stochastic, you need to do some other thing. You need to like somehow distribute it. But for if you're, I mean, it's I think it's like it's like it's not like our idea. I think in previous works there was something like that people just split like in function to, I don't know, to maybe to 2 workers, and other workers they just don't do, like, they don't have any information. So
Okay.
Just to add to this a little bit, so we consider, in some sense, because we consider L-smooth non-convex regime, in some sense, it may seem like we're considering some difficult regime because it's non-convex, but in fact, it's the simplest regime for us because we don't need acceleration, because acceleration will not do anything in this regime. And this is also one of the reasons why these things cannot be improved. So as soon as you start considering convex regime, then you would need to have some kind of acceleration if you want to have optimal methods. So somehow we benefit from the non-convexity or from the inability to accelerate problems in the worst case for that class of problems.
I mean, I didn't mean acceleration exactly, but just the fact that this improvement is only comes from the stochastic noises. So you somehow overlap the timings of in a synchronous SGD. You somehow overlap the timings. That's roughly how you get improvements in the time complexity. But once you remove that stochastic noise, somehow this overlapping does not give you any like improvement in the time complexity. But that was the a bit counterintuitive part. Of course, in non-convex case, there's no guaranteed acceleration in terms of momentum, but I thought the overlapping could also happen in that case.
But this is because maybe the way you should think is that as soon as sigma is 0, you don't need another stochastic gradient apart from the first one from any worker because there's 0 information content in it. So that's really the intuition.
This is data heterogeneous case, right?
Yes. But if you get one stochastic gradient, which has 0 variance at xk, that's the gradient at xk, and the second gradient xk is just the same vector. So only in the stochastic case, you get new information from another sample. But in the deterministic case, you get new information. That's why the optimal thing to do, even intuitively, is to ask everybody to give you just one stochastic gradient, which is the local gradient, which means you just run gradient descent in the end. Right?
Okay, so this overlapping in the stochastic case becomes like a full gradient, and that's all.
Exactly. Not overlap. I mean, it just means you ask everybody, send me one stochastic gradient, but the stochastic gradient is full gradient because sigma is 0. And then you don't need to ask again. I mean, you could, but it doesn't make any sense because you just get the same vector. Right?
Okay.
So that's the reason. So in that case, the optimal thing to do is ask everybody, send me your gradient, and then you average them, and you really just run gradient descent in that case. So one way you can think of this improvement is that the stochastic gradient contains some information, but not all information. And the improvement comes from the fact that you reduce the variance enough for this stochastic term to somehow, maybe not be dominant and kind of match the deterministic term.
Then in the interest of communication, wouldn't it be optimal to compute the full gradient and communicate once rather than compute stochastic gradients and then communicate in between? I mean, of course, once you add the communication heterogeneity.
Okay, so then we have the Shadowheart method, so we can look at it. So in this case, we can consider stochastic gradients. And in stochastic gradient setup, you actually have to you have to reduce the variance, and that's why you have this BI there, right? But if you were to now, I don't remember, maybe Sasha does, I don't remember, but let's have a look. Let me try to think. What would happen in this case if sigma square is 0? What would happen with equilibrium time? Do you, Sasha, remember what happens if sigma square is 0 with equilibrium time?
So are you considering homogeneous or heterogeneous? Or it doesn't matter?
Well, I'm considering homogeneous because heterogeneous we don't know. So this is homogeneous setup, right? So heterogeneous we don't know.
No, I think
I'll keep
when you don't have noise.
Yeah.
No, when you don't have noise, I think this method should wait for the worker who has like the smallest sum of communication and calculation. So because like every worker, if he wants to send it to the server, he needs first to calculate and then to send. So you need to wait for some worker that has this
yes, but in this case, it will also reduce to gradient descent. It will just finally implemented gradient descent. Right? Because this compression, I mean, if you just think about it, everything will then be just gradient. This will be just gradient. So it doesn't make sense to have BI of them because it's just gradient, right? And the compression, it doesn't again make sense to compress. I mean, you could compress, but then you would need to do it multiple times. So let's say you do rand 1 compression. If you do D times to the same gradient, that's the same thing as just sending the gradient. It'd be kind of the same cost. So in the end, you would just get gradient descent as a method.
No. I mean, if sigma 0, then then even if sigma 0, then it also can make sense to compress if your communication is like slow. So that's
right. Let's see. Let's see. Mi will be, yeah, because T star will be finite. Theta i's will be finite, so Mi will be finite and might be smaller than D. So in the end, yes, it will not be gradient descent necessarily. Depends on the theta I. It will be some sort of compressed gradient method, where the compression really depends on the communication speed. So if the communication speed is very fast, then this will be closer and closer to gradient descent, and it's very, very slow. It'll be closer to some kind of compressed gradient method. But to be honest, we didn't think about this extreme case fully clearly, so we would need to double check.
Yeah, thank you very much.
Any other questions?
I have one. Have you also considered the case where the calculation and communication times can be random? Like you can always, and also like, for example, if also random and specifically like also Gaussian, so they can be unbounded, but
So
the largest value.
Sasha has a paper, single authored paper, where he considers almost arbitrary arbitrary computation patterns. It's not even random, but varying almost arbitrarily, even continuously throughout time. So maybe Sasha, you can comment on this.
Yes, I mean the short answer yes. I mean the idea. I mean it's. I don't think that I can explain it briefly. So I think the best thing I can do is only refer to it.
Maybe you can
Yes.
send it to the paper. So
yeah, I mean, or
we
to the
consider,
post. Yeah.
Yeah, so we considered that Sasha considers in this paper, and then we were inspired by this work and some other works to
I think something related
do
also
something similar in this Ringmaster ASGD paper. So here there's also
Mindflayer, I think, related.
And Mindflayer has random computation times, and here there's also all kinds of variability in the computation times. Not just fixed, but they can vary in various ways.
Okay, great. Thank you. It's very interesting.
But there is one tiny difference between the setup in Mindflayer and Sasha's paper. And the difference is that in Sasha's paper, Sasha assumes that you cannot control these times anyhow. But for the Mindflayer, so it's random variable and you somehow can control it. So maybe when you send the gradient, and because of the network, it doesn't arrive to the server, you can maybe resend it. In that case, you just do the coin, you flip the coin again, the random variable. So in that sense, you control the time.
Okay.
Okay, so I will rephrase this differently, just for extra clarity. So in this paper that Arto was leading, Mindflayer, we can ask a worker to start computing stochastic gradient, but we can also kill that process anytime we decide. As a server, I can ask a worker, start computing stochastic gradient, then I wait for a minute, let's say, and if the worker is not done, I can just say stop, and I can ask the worker again. And this is not what you can do in Ringmaster ASGD or this other work of Sasha, but in Mindflayer you can do it. So it's extra trick you can do, and because you can do this extra trick, then you can get somehow more powerful method in a regime where you can do something like that.
Yeah, it makes sense, because if there is variability from time to time, that I can say, okay, maybe like this time, like a specific user or client has a very like bad realization of delays of computation or communication times. I would say it's not that bad because it's not fixed. That maybe in the next round it will get much better.
Yes, that's exactly what we do in Mindflayer, and in Ringmaster we just accept the fate of whatever happens with the compute time, whether it's random or not. We're not restarting anything. We just accept the time. and try to adapt to it. So I can see another comment in the chat. This is just a link to the paper. Yeah, so I should actually, for future versions of this talk, I should add Sasha's paper to this list. Too bad I didn't think of it before. Okay, so it seems like this is all that I wanted to say. Maybe if there's like one or two more questions, I'm happy to answer. Otherwise, I already took quite a lot of time. I can see that half of the people already left, which is great. That means they listen to my advice. Good.
I have one question about Shadowheart. So in Shadowheart, every time you communicate, you have to do this compression, right? But have you considered that instead of doing the compression with this omega parameter, and so you do this BI computations, you send one bit to the server, and you say, so you did the computation, and you keep storing this MI BI gradients, and then you send whenever, I mean, you did enough, and you compress this full vector, and you send it to the server.
I don't really know what you suggested. I didn't follow you. What do you mean? So you sum up these BI stochastic gradients and you send what? One bit?
Yeah, you send one bit. You don't compress. You send one bit saying that the server, I did BI gradients. And then you do MI times BI gradients overall. And then you send the whole vector.
But why do you send the bit? What is the bit? What is the bit good for to the server? Why would the server want to know?
Because I'm assuming that you are sending this compressed gradient so that the server knows that
no, it's nothing to do with the
finished.
No, it has nothing to do with the knowledge. No, it's not it's not for the knowledge. It's just it turns out it's better to send multiple compressed sums rather than one compressed sum, or rather than multiple non-compressed sums.
No, but I'm thinking from the Rennala point of view, because you're saying that in Rennala you have to send every time you compute a finished gradient, but it's not the case. You can compute the gradient, you can still store them, but you can send one bit saying that the server you finished, and whenever the server receives B bits, and then you can ask all of them to send you the sum of the gradients.
No, but there's nothing to do with the server not knowing or knowing. I mean, you don't even have to send any bit because the server can assume that you will send something. So you don't have to send any bit, and you just send at some point a message, right? So server can just
know. They don't know when.
It doesn't matter because this method is fully synchronous. So it has to get the message from everybody, right? This method is not going to ignore anybody. So,
okay. All right, thanks.
So the bits really don't matter. I don't understand quite the idea. So it's not about communicating to the server that, yes, I'm still doing something, please wait for me. There's not the purpose here.
No, but if you just forget about communication, and I mean, forget about the compression and think only about Rennala, let's say, and you want, in Rennala, you want to reduce the communication. So how I would do that, I would, instead of sending gradients, I would ask the clients to store them and then send whenever I feel like I have enough, and enough would be B. So, but there would be some, I should know when this B is collected, and knowing this would be them sending one bit of information to the server. See what I mean?
Yeah, well, I understand part of what you mean. I mean, it's true that in some sense, if tau I for some I is very large, then maybe let's say the BI is even going to be like 0, right? So, that can happen, just like in Rennala. This is the data homogeneous regime. So it's possible somebody is too slow. I want to retract a little bit. I was just considering the regime where maybe everybody is useful. But here, it's not that we compressed after every BI in order to send a signal to the server that we're doing something. Like that's not the purpose of the compression. The compression is there because otherwise you would need to send D entries of the gradient, and D could be huge, and this is going to take a lot of time. So the compression is there to introduce, to reduce the communication load and not to signal anything. But here we're not quite explaining when talking about Shadowheart from this perspective, how should the server know that maybe it would not get some updates from some workers. So he's written in kind of a cryptic way. But I still don't understand beyond this kind of signaling purpose of sending this bit. I don't understand what you're trying to propose beyond this just being signaling.
Okay, let's say MI is very big.
Right.
So if you send compressed vectors, which are like smaller than D, but overall it will be bigger than D. So maybe in that case would be better to store all of them and send one D vector at the end. So wouldn't that be better?
Yeah, but the server can know the MI. Like we can assume the situation. Assume the situation where tau star is known and tau I is known. There's no adaptivity to anything. All these parameters are known to the server and to the workers. Let's say it's like simplest possible scenario. Then the server will know it should be expecting MI compressed messages and so on. So then we don't have to, tell the server anything. It just knows it should be expecting these, right?
But there can be one difference, right? Like if you have some communication budget, right? For example, you can like for all the MI communication rounds or communication times within like the specific round, you can use up to that amount of bits. So maybe you can like use the higher if you do like the averaging of the stochastic gradient yourself in the client, then it can then use like higher precision because it can use the whole bit budget for the less time that it sends. Like send only one time with high precision.
Yeah, so here we don't have a communication budget.
Yes.
So here we have the goal of minimizing the time complexity, and time complexity consists of computation and communication complexity. And we kind of add them up. We treat them equally. But it's possible to extend this idea by saying that in fact, you don't want to treat them equally. And maybe you say that communication is more, important, or that actually you have a bound on how much you can communicate in one iteration for some reason. I don't know what the reason could be, but it could be some reason. And then these things would need to be adjusted. Okay, thank you, Sergey. I'm responding to chat, not to you. Sergey said, sorry, it's the work evening lesson. Okay, thanks for attending. Okay, so Arto, I guess we'll need to talk about this in person because I'm not fully grasping what you have in mind, but we can definitely further think about it. Okay, then I would like to thank everybody and thanks Sam.
Thank you, Peter, and thanks everybody for very insightful discussions. Yep. Thank you all. Have a great rest of the day. Bye-bye. Okay. Thank you.
Bye.
Peter, please send me your slides, and I'll there was a question. We always post the slides and also recording after the talk, and that's going to be on our website. Thank you again. Have a great day. Bye-bye.
Yeah.
Thank you.